go ahead and just stop me whenever you need to. But I wanted to go back in chapter 12 and just review a little bit. Don't want to go too crazy with review. We do record these after all. I will say again on page 166, he's giving you a good hint as to what you need to know for the big tests. For this chapter, it says the remainder of this chapter describes different types of two-dimensional ultrasound transducers. Specific attention will be paid to 5 characteristics of each transducer style. So he's telling you these 5 characteristics are free game. You're going to be tested on them. The shape and the number of active elements in the transducer. So how the elements are arranged. We've only talked about a couple of arrangements so far. Automatic redirection of sound beams to create an image. That's steering. That's what he's talking about. Automatic redirection of the sound beams to create an image. He's talking about how does the beam steer, or does it steer, or whatever. Focusing of each sound beam. Some beams are fixed, some are not. Shape of the two-dimensional image. Do we get a square like we do with our linear transducer? Do we get something more of a curved top, or do we get a triangle? That we'll talk about real quickly with the mechanical transducer and linear phased arrays. And the consequences of a damaged or non-functional active element in the probe. I don't know why you make a big deal out of this. I mean, why do we, if it's broken, it's broken, right? But I think by understanding, when you understand the consequences of having one element broken, you understand a little bit more about how that transducer is working entirely. Because, like, for instance, on this one over here, if this is a mechanical transducer and one is broken, we're done. Okay, let me. All right, so I've drawn a particularly ugly transducer here. I usually take a little more time for this. But let's just review a mechanical transducer. Mechanical transducers have one element. Let me zoom in. Hopefully my writing will improve a little bit here. One element. That element is spun around in a circle at a high rate of speed. As it's spinning around, it spins around once, it fires off, the current, where the current location of this element is, as this is spinning around, it fires off a pulse of sound, receives a pulse of sound back, spins around again, does it again. Except it doesn't do it in the same spot every time. So if I were to make less of a mess down here, and actually get rid of my little transducer as it were anyway. Well, whatever. So at one point in a spin cycle, the element's over here, it fires off in that direction. Goes all the way, goes all the way around. Next time it's here. Goes all the way around. Next time it's there. Next time it's there. And then it starts over again. Here, and there. And obviously it's going to be more than 4 beams of sound. That wouldn't produce a very productive image. And of course, every time that happens, there is a, whoops, it's a particularly ugly waveform. There's an echo that comes back. And so this produces, because basically every single beam is coming from more or less the same point, or very close to the same point. This is a small diameter transducer. You're going to have you're going to have a screen that looks like this. Little pizza with individual beams. Yeah?
So is it the fact that the electricity is going over and then it's missing it the next time it comes around, or is it like a chain reaction where it hits one first and then hits the next and the next and then works itself all the way around?
Well, the engineers have figured this out, that they're timing the element. They know exactly the speed of rotation of the entire mechanical transducer here, or this whole they know exactly the RPMs, and so they're timing it so that this is the first one, second, third, fourth, and then they start back to first, second, third, fourth, and basically you get 1, 2, 3, 4 beams here. Once again, obviously it's going to be more like 50, 100, 200 beams.
So it's kind of working like an LED light?
Yeah, it's actually working like a laser show is a good example. Kind of. Laser shows use mirrors, but it's the same difference. Oh, actually, that's one thing I didn't mention. It's not mentioned in this book. It's mentioned in other books. You could actually have a stationary element, and what's spinning is not the element, but an acoustic mirror. And so you could actually aim these beams using a mirror too. That's another way of doing it. But we don't need to know that. Just know that the mechanics are that it's spinning very rapidly. One disadvantage is the distance between beams in the far field just keeps getting wider and wider and wider, whereas the distance between beams in the near field, they're very close. In fact, they probably overlap in the near field. So in the far field, there could literally be a small object, that's not seen. It's just totally missed. There is an algorithm that the computer uses to kind of fill in the gaps, but it's only guessing what's in between the gaps, doesn't really know. So that's a disadvantage to these. But they're very small footprint, so they're great for getting through ribs. If we're looking at a baby's brain, it goes right through the, I want to say foramen, it's not a foramen. So, well, the soft spot. The actual term is lost to me right now, but the soft spot. They used to use these on transvaginal ultrasounds. So, if you wanted a wide angle of view, let's see, we had the transducer more or less shaped like that with the little little beam like that, and then that beam was able to be sent out, and as this guy is spinning around, it sends off a beam this direction and that, and we're able to get a nice wide angle view of the contents of the pelvis, uterus, ovaries, and everything. I haven't seen one of these in a long time, so they're pretty much out of date as far as transvaginals go. They're going to multi-element transducers, which, so it's a very tight, it's called a curved. Well, it's actually our vaginal transducer is a curved, just like the big curve that we all have on our machines that you would use for abdomens. The vaginal is a very small version of that same thing. It's still a curved. Internal focusing, external focusing, but in any case, fixed focus. Fixed focus. And mechanical steer. Did I just use the wrong steer? S-T-E. Whatever. No, I didn't. It's two E's. Anyway, so do we answer all the 5 questions? Shape and number of active elements. 1 element, and it's a disc. The actual element is a little disc shape, like small little coin. Automatic redirection of sound. In other words, steering is mechanical. Focusing is fixed, either external or internal. Shape of the image, and the consequences of a damaged element. If you damage the one element that you're using, you're done. No picture left at all. So then we go into arrays, transducer arrays. And these have many elements. I'm just going to go straight over and use this picture that I had for, way over here. I'm going to say, no, we're not talking about one element. That was yesterday's review, was one element. But instead today, we're going to have many elements. Many elements doing the same thing that a single element will do, except now the single element, we don't have any control. We cannot electronically steer. We cannot electronically focus. We can mechanically steer it, but we cannot electronically steer it. Here, we actually can focus and steer electronically. So this is basically, in general, this is an array. Each one of these has its own separate wire going back to its own specific circuitry in the machine. Each one of those wire, circuitry, and element is called a, I need your help because it's, oh, I know what it is. You guys anyone know what it is?
Channel? Is it a channel?
Right. Channel, 2 ends. It was pointed out that Chanel number 5 is 1 end. Each one of those is a channel. Each one of those can be individually fired, although you would never fire an individual in an array. You would never, at least not completely by itself. Like if I chose to fire only this one, I would have a beam that spreads out. It's not even a beam, it's just sound that spreads out in every direction. That wouldn't do us any good. So we use multiple elements at or almost at the same exact time. There could be very small changes in when exactly each one of these is stimulated, but that's steering, and that's focusing as well. So on a linear phased array, that again is a small footprint. These guys are used for getting between the ribs or getting in the soft spot. Fontanelle, that's what it is, the fontanelle of the head. Because they get into small spaces. And once again, because because every single element is used every single time. Slight differences in timing, but still every single beam is used every single time. Because of that, we get a waveform that's shaped like this. Even though that's, like I said, I have a hard time reconciling in my head exactly why let's say 2 centimeter and a half face or aperture is going to come down to an absolute point like that. I have a hard time reconciling that in my head, but suffice it to say it does. So
I get how it could, considering that where the beams are being created from, that the programming wants to say this is the start point, and since it's a beam, it spreads out, which leads me to the question of the channels. Let's say we've got a transducer that's got 20 elements in it. So that's 20 channels. Are there transducers in there where you could change what channels are being used to narrow the field?
well, it's all done automatically, but yes. So this is this one that we're describing now is a phased array. Phased simply means that's basically the same as saying timed or timing of the elements. The larger elements, our curved element, well, actually our linear element, our linear transducer as well, they're not only phased, but they're sequenced. So you use maybe 10 elements, and then a different 10 elements, and then a different 10 elements. So that's changing every time. On the phased array, every one of these is used every single time. And it ends out having a triangle shape like this. Oh, shoot. In order to get rid of that, I need to get rid of all I just wrote. Okay. So let me write that again. Phased array, same thing as saying a timed array. Every single one of these channels is timed differently, but let me get back to that page. So shape and number of active elements. Okay, 100 to 300. 100 to 300 elements. The width of each element is 1/4 to 1/2 of the wavelength. So the width is 1/4 to about 1/2 of one wavelength. Oh, interesting. So if it's 1/2 the width, then it's a perfect square, right? Because the thickness is 1/2 wavelength. So we know that for the fundamental frequency, that's 1/2 lambda, 1/2 the length. Remember when I draw my little element like this, and then so that whole green line there is a full wavelength, and this is 1/2 of a wavelength. So yeah, I never thought about that. If the element is 1/2 wide and 1/2 thick, then it's a perfect cube. Anyhow, learn something new or think of something new every day. Okay. Let's see. Width is fan or sector shaped. 1 to 300, quarter to 1/2 wide. Electronic steering, and should say it on the next page, and electronic focusing as well. So this element, or this array, kind of has, I don't know if it was, like I kind of did this by accident. I was just drawing it really quickly, and I drew a wavefront that is, well, let's say it's just very slightly focused. Let's say it's focused to that point. That was just kind of a happy accident the way I drew that. So that means if I did purposely bring the focus up closer, that means that as a matter of timing, this one and this one were first, second, third, fourth, fifth, and then these middle ones were the last. They timed such that they went outside in. By timing it outside first, inside last, you've brought the focus closer to the transducer. You've created more of a curve here. And if we wanted to steer in that direction, we would have to make a curve that went like that. In other words, it would be going on the screen from right to left as far as our timing goes, and that would bring us that way. I could draw that again if you guys need to, but let me keep moving forward. So it's electronically steered, electronically focused. That's 2 more. Oh, and the damaged piezoelectric crystal on this, not too bad. Let's just damage this guy. So that element's no longer working. And if we're really careful, let's see, let's just say I got rid of.
And with damaged elements, that can end up causing artifacts, correct?
It can. You know what, guys, remind me next week to show you the damaged elements that we have in the room currently. We have 2. We have 1 linear and 1 curved, each with a damaged element. And honestly, it doesn't even cause any problems. So, because if you can see right here with this damaged element, we're missing some waves here. But soon, with the other 100 or 300 elements that are working, you don't even notice it because of all those other waves they're gonna constructively interfere with each other, and the fact that we're missing one right here is barely going to be noticeable. However, the book does say inconsistent or erratic beam steering and focusing can occur. I'm sure it can. And so far it hasn't with ours, but I'm sure it can. Okay, then we talk more about steering. So I guess we could we'll just review that. Yep.
When it comes to the elements themselves, I know that if they're heated up beyond the Curie point, it can damage them. How fragile are they? So let's say you end up dropping the transducer. Are they that fragile, kind of where they'll like crack in half and whatnot?
Yeah, we really don't want to drop those transducers. They are. They're originally made from actually I could draw it right here. They're originally made from a single slab of piezoelectric material, and then they're cut it's easier to do it this way rather than making tiny ones and then trying to put them all together. They're cut. Each one's got to be a little bit separated from each other, so they're not stimulating each other to ring. You want to have control over each one of these. But yeah, if you drop the transducer, you have a good chance of ruining that transducer, or at least breaking one of the elements. And I'm sure that's what happened with.
You said they have to have a little bit of a gap in between. If they were stimulating each other, would that be caused by harmonics?
Well, yeah. If you take two tuning forks and you bang one tuning fork and bring it closer to the other one, close to, not touching, just close to, and then you muffle off the first tuning fork, you'll hear that second one ringing. And that's not the piezoelectric effect. That's just simply mechanical energy going through the air to that second one. The same thing could easily happen here if we're not careful. So these things are made, they're not just like thrown together, in other words. They do have to be insulated from each other somewhat, because yeah, you don't want, let's say, like when that one rings, you don't want this one and this one to start ringing too. You want to have total control over your system, so that the only one ringing is the one that's stimulated. So when the voltage is, let's see, I'm going to put V with an E minus. That's basically voltage in electrons. I don't know if that's correct way of doing that, but I don't care. If you think about, every one of these has potential for voltage, and so you stimulate one, and a little voltage. Let's do this. I like my little E's. That's going along, comes down, and pretty much at the speed of light, it's going to hit that. The timing in the wires mimics exactly what the element will do. I'm sorry, the element will do. It mimics exactly what the beam will do. So if we time it so that the outside is first and the inside is last, and then all the others kind of follow suit, we're going to create a beam with the same structure. And of course, what we've done here is focused. So that was a focus voltage. We told the machine, hey, bring the focus up to here. So the machine said, oh, okay, that means I'm going to stimulate these outer ones first, and then 5 microseconds later, I'm going to stimulate the last ones. So there's a progression of voltages. On the same token, if we want the beam to steer in this direction, well, then we're going to stimulate this one first. Let's say unfocused. If it's unfocused, we do that one first, this one last. So it's simply steered, and we get a wave front that's going off in that direction. So that voltage coming down from the machine mimics exactly what's going on here. Now, we're almost always focusing, right? There's always some kind of focus. So we could steer in the same direction, and then rather than making a straight line across, we could even curve it. So still steered, but also focused. So now we're going to have a wave front that looks like that. Focused and steered in that direction. And of course, well, then we get the multiple focuses. I think that's the next thing we're going to talk about. So the book shows different degrees of focusing, different degrees of steering and focusing. On page 176, it shows what happens if you were to try to let's see if I'll just draw it. Let's say your natural focus let's just pretend our natural focus is right here. You try to bring the focal point down to there. Can't be done. Because anytime if you curve it, when you curve it, you're actually bringing the focus up. So you say, okay, well, I'll do the opposite. I'll curve it in this direction. So that the middle the middle elements are being stimulated first and the outer is last. Well, what does that do? That creates a wave front. Let's see, I'll try my bubbles here. That creates a wave front that's perfectly wrong. Totally unfocused. This is never going to come back to a focus. That wave front is forever going to go off to the right and to the left. It's always going to spread out. So that's why we cannot focus beyond the natural. Okay. So that's kind of all review so far. At least I hope it looked familiar. The next one is multiple focus. Now, if you think about this, think about that. How do you get a? I'm drawing way too large here. Let me zoom in. Okay, so think about that. Multiple focus. So you have a beam. Let's build my little transducer, or my element. Actually, my multiple elements. Still in box. And I create a beam that looks a little bit like, I focus again, I focus a third time. Now, what we know so far about how this works, did I just erase? I shouldn't have erased that unfocused, but I just mentioned, we just talked about how once the shape of this beam once it comes down and starts to bow outward, there's no stopping it. It will forever go away. And what happens here, let's do a focus. The beam's coming down like this. It's curved. It's actually coming down to a focus. And then right at the focus, it more or less does this, and then it'll start to spread out. Once that beam starts doing this, there's no stopping it. It will never come back to a focus again. So how do you guys think that we're able to create a beam profile shaped like this, where we have a focus, and a focus? 3 little triangles on the side of your screen showing where the focal points are. What do you think? How would that happen?
Would that be from the channels that are used to create the sound waves and the frequency being thrown through them?
It's not the frequency.
Does it have to do with the pulse repetition? Like one pulse is going to one focus and then the alternate pulse goes to another and just back and forth?
Yes. So, zoom in a little bit so I can attempt. Actually, let me get my little, son of a bee. There needs to be like a little push button where I could just, oh good, you're right there. Who would have thunk it? All right, I just need that little cheater to help me with this picture. So yes, multiple beams. If you're gonna have any more than one focus, you're gonna need more than one beam. So if you have, let's say our first focus is right here. That's one beam. But then we have two focuses on our screen. We've asked for two focuses. So then we have a little, let's say a little purple focus down here. Of course, I've made this difficult. So then, we have another one. So let's put a third one in. We'll have another focus right here. So now, in essence, what we've created is, let's see if I can do this with a third color. In essence, what we've created is a long focus. Ooh, kind of like that. This isn't one beam. It acts like one beam, but it's not. It's actually 3 beams or 3 pulses. Let's see, I was gonna say pulses. 3 pulses, each focused. Good Lord, that looks like focused. Each focused at different depth. Makes one beam. I'm gonna put that in quotes because it is one beam, but it's pulse, pulse, pulse. Each one creating its own set of echoes. Remember, pulse repetition frequency. Even though I have 3 pulses making one beam, we still have to wait. We have to wait for all the echoes to come back before the next pulse comes down. So it makes one beam in quotes with a long focal zone. So we could say like this, whole area is the focal zone. Whereas for any one of these, that's the focal zone for the green. Let's see, purple. This might, yeah, okay. Close enough. That's the focal zone for the purple, and then for my blue one, that was the focal zone. But you see those 3 focal zones overlap. So you can imagine, and remember, why do we have focal zones? Because of lateral resolution. An object here and an object here, if they could be seen separately, in other words, you know what, I make that object a little bit farther away. Let's say an object here, and then one all the way over here. Do that one last time so I can show you something else. There we go. Those 2 objects are not in the beam at the same time, therefore they could be seen separately. If they're in the beam at the same time, they cannot be seen separately. If we drop these all the way down, now those 2 objects, same distance apart, but they're both in the beam at the same time. We're going to see a smeared echo. This is going to look like one big echo rather than 2 separate echoes. So, gosh, I mean, so why don't we have 3 or 4 or 5 focal points every single time? Why don't we always do that? Anyone know?
I mean, I feel like the easy answer would be it would put too much stress and kind of lag the machine, but that's probably not what you want.
No, actually, that's pretty much right on. It's time. We're talking about one beam, but it takes 300 beams to make an image. So those, you know, so normally with one focus, it's beam, 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 300 times. You get to the other end and you start over. Beam, 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 beam. Start over, start over. Now, if we have 3 focal points, it's beam, 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 next line of information. Beam, 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 beam. So we've tripled the amount of time it takes to create an image. We haven't really spoken about frame rate yet, but the frame rate is the time it takes to create your picture on your screen. The more pulses you have, the more focal points you have, the more it's going to take. In fact, for every focal point beyond 1, it doubles. So the time it takes for the whole screen to be created with 2 focal points is twice as much as 1. With 3 focal points, it's twice as much as 2. Yeah.
Or is it 4 times as 1?
Don't confuse me.
Well, I'm wondering if we're looking at the aspect for each focal point that goes beyond the first one, does it continue to double on each one?
Yeah, I just caught myself in a mathematical conundrum because I can't think on the spot when it comes to math.
Because-
I do believe it's doubled every time.
Okay, so if the second one would be
No,
doubled,
it wouldn't be doubled. It takes between 1 and 2, it's definitely doubled. Between 2 and 3, you've already doubled. But it's going to take more time. I'll have
do you
to.
double it past each focal point though?
Yeah. I have to work that out, or ask my daughter after class. Though I can't do it on the spot. But it's definitely every single time you add a focal point, it's going to take more time to produce an image. So I'm jumping ahead a little bit, but if you're doing a thyroid, which is, let's see, you guys can see me, right? Which is, that far below the surface of the skin. Well, the go return time for a single pulse is, well, it's only 2 centimeters, so 26 microseconds. You have a frame rate that's near 100 at that point, 100 frames per second, which is way beyond our comprehension of being able to see it. So when you're doing a thyroid, go ahead, put 4 or 5 focal points in. It's not going to slow you down. Or the imaging is so fast anyway. Because remember, it's depth too. Pulse repetition frequency is decided by the depth. And if you have a very shallow depth, you have a very high pulse repetition frequency because you're not waiting very long, 26 microseconds. It's just going back and beams are going out, echoes are coming back at blazing speeds. So go ahead, put a few focal points in there. It's not going to hurt. It's not going to hurt your image at all. It's going to improve your image. But if you're going all the way down deep into the liver, and now we have 15 centimeters, we have to pulse, wait for all of those echoes to come back, pulse, wait for all those echoes to come back, and you could imagine now you have 3 focal points. You're waiting, well, let's just say 3 times as long for that image to appear. So for that image to be created. So when you're going deep into the body, I usually use 1 focal point deep into the body because I can't stand. What happens? There's a time. It's the timing of the screen. If it's not reproducing a new screen fast enough, and you move your transducer, the whole screen gets blurry. It's actually a little nauseating to look at. It literally makes me seasick. So I have to have a high frame rate so I don't get seasick. Okay. Now this next one, 11 o'clock, 11:10. All right, let me just make sure I didn't miss anything. Focus is considered the waist, just for example. Boy, only like two small paragraphs for that. It's actually it's kind of a hard thing to explain. So I am still drawing way too big. Okay. I need some space here because the next thing we're going to talk about is the flip side of this, and that could be a little tricky. So we use, let's just look at this again, Huygens wavelets to our advantage. When we have many elements, we can effectively change the shape of that beam, and we could bring the focus up to where we want it to be. But then there's an opportunity for a second focusing. Takes time to get another page going. I could. So let me draw in another. What color is that going to be? That's going to be the color of an eraser because that's what the mode I'm in. Okay, my multi-element transducer, it produces a pulse of sound and it's focus. Let's just say a single focus. The pulse looks a lot like this guy up here. And it comes down and hits a couple of objects in the body, a couple of tissue interfaces inside of the body. Yes, and let's see. I'm going to have one of them kind of shallow, and the other one's it's more or less, let's kind of make it more or less identical. That's deeper. Actually, let me make sure that I say everything correctly. The question introduces the concept of dynamic. So we're talking about this is going to be dynamic. Receive I before E, except after C. C focus. Okay. During transmission, however, that's only part of the story. Focusing may also occur during reception. Multiple neighboring elements probably outside these elements create electrical signals. More accurate image can be variable time delays. Okay, so this is complicated stuff right here. And now that I just wrote that, I'm going to erase it because I need room up here. Dynamic receive focus. So I'm just going to draw the echoes in here. So sound beam comes down, and this guy is not going to act like the echo doesn't act like a laser beam of sound. The echo acts like sound. It's going to spread out. So it's coming back like this. It's spreading out. Huygens wavelets don't count on the way back. They only count on the way in. Let's do that last one a little more carefully. Okay. Let me draw the second echo in. I'll just leave it like that. Okay. That makes sense, right? We're no longer, the echoes don't act like Huygens. They act like any other sound source. They're spreading out. It's one reason why the echoes are so much weaker than the beam itself, is because they spread out. It's one of the reasons. On the first echo, on the first object, the elements that are going to be stimulated are these. All of those elements are going to hear that object, if that makes sense to you. That's what's going to be stimulated. They're going to hear it. And in fact, there's a little bit of a timing. You could see by the curvature in this wave that, let's see, this one's going to hear it first. These two are going to be just slightly behind this one. 3, 3, 4, and 4. So remember, this is the opposite. This is coming back up, but there is a curvature of the echo simply created by the fact that it's spreading out. And that transducer is going to hear, those individual elements are going to hear that echo at very, very small interval differences, maybe microsecond differences, but they're still going to hear them differently. Then we have this guy where, let's draw the last one again. That's going to be stimulating, well, realistically, let's just say, all of those elements are going to be stimulated by that one. Once again, looks like this one would be first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So starting kind of in the middle of the of there, you know, it's going to start here. This is going to be the first part to hear it, and then the rest of them are going to hear it microseconds later. So remember, this machine has remarkably good timing. It is a range finding machine. So on a range finder, you have to have a super accurate watch. And the watch on this machine is very good. It knows that if an object is 13 microseconds away, which is the same as saying 1 centimeter, it knows the spread of that echo will average out to be about that size. If on the, let's make it 39. At 39 microseconds, that is equal to 1326, yeah, 3 centimeters. It knows most of those echoes are going to spread out that much. By timing the listening, by saying, okay, at 13 microseconds, we're going to put a time frame we're gonna oh, how do I say this? We're gonna delay outside elements, we're gonna delay inside elements enough for the outside elements to catch up. What did Kurt just mean by that? Because as I was saying it, I'm like, what do I mean by that?
So the timing on the outside elements is going to be minuscule compared to what's in the middle.
So, yeah, well, it'll definitely be minuscule. So let's think about this. We have our channels. Let's just use black ink for the channels. And we're only going here to here for this one. If we do not focus on the receiving end, this element here was our, just want you to be green. This element here is the first element to hear anything, and then further out, there's microsecond changes in when they hear it. Just like going in, the voltages created by the element as it's being stimulated by the sound of the echo is going to create a curve. Just like, except now remember, now we're going this direction. The transducer, right? Electricity creates sound, sound produces electricity. There's actually a curve going back. And so if the engineers have figured out that, look, you know, we know at 13 microseconds, we know that the average spread is going to be, you know, whatever. I can't even imagine how they know this, but they know what the average spread is going to be. They know that what the curvature is going to be from a typical object in the body. It's going to create a curved wavefront of electrons going back to the machine. Just like in the other direction, there was a curved wavefront. Now there's a curved wavefront going back. By timing it, by dynamic receive focus timing, somewhere up here, let's just create a little, I'm going to create a little box in here. This is some kind of electronic component. I actually should know what it's called, but I can't think of what it's called right now. But this guy electronically, no, not the multiplier. It's the I can't think. That's okay. We're not to that part yet anyway. Electronically, it's going to take that curved and it's going to straighten it out. Whoops, that's not what I meant.
So it's going to take it from what it's perceiving as a three-dimensional and turn it into a two-dimensional image for us?
Well, it's taking the, just because the echo coming back is curved doesn't mean that the thing that created the echo is curved. The thing that created the echo, in fact, I could redraw the object down here. I could redraw this object and say instead it was a gotta get myself out of.
Because that curve is going to be determined by the speed of the sound wave hitting it and reflecting, correct?
I'm sorry, can you say it again?
So the curve is determined by the speed of the echo that's reflected. So if each one's, you know, just a microsecond off from each other, the first one to hit it's going to come back. It's going to reflect first before the next one, which will end up causing a curve.
I think you're saying it right. Well, here, let me just say this. This is now my object. Whatever this is. Looks like someone ate a microchip, but that is now my object. This object has a totally flat surface that the sound beam bounced off of. The echo that comes back though is not flat. Because of its the way it's the sound moves, it curves more. The farther we go, the more it's going to curve and curve and curve. And so what the transducer initially sees, what it thinks it's seeing, the transducer, it thinks it's seeing some kind of curved surface. But it's not curved. It's just that's just how the sound travels, how it moves away. And so what happens in here, well, I forgot what this is actually called, but we'll actually call this the dynamic receive focus machine. It will take that curve, flatten it out, or take the timing. How about this? Actually, this is a good word for it. It removes timing errors.
So it takes out the difference in the time from each electron reading back to it.
Yeah, it's going to remove those timing errors. And then there's
All right, I made you sound like Darth Vader.
Do I still sound like Darth?
No, not now. Damn it.
You're over it early, Lisa.
I think it's me. I think I'm the one that causes it. I'm sorry, Kurt.
Well. How do I sound now? Don't say anything.
Not any better. It's worse.
Shit. Right. Well, it's 11:30 anyway.
All hail the Empire.
I'm starting to get real distorted again.
Well. Guys.
Thank you. Bye.
Thank
All right.
Thank you, bye.
Sorry, Kurt.
It's all your fault.
Probably. Just blame the old man over here.